What's up, everybody? Thanks for tuning into the stream. My name is Logan. If you're new to the stream, you could also call me Techgician. It's up to you. And today we're going to be discussing quantum computing. Now, I'm not an expert on quantum computing, but I am very interested in learning about it since it's a relatively, new technology. Yesterday we talked about cryptocurrency, which is still relatively new in the beginning stages, even if it's, considered to be 10 years old. It was still, a relatively new topic. It takes quite some time for these kind of technologies to really take flight. And so is quantum computing. It's been talked about, I think, for the past 5 years, maybe a little bit less than that, and has now really started to take kind of like an actual acquirable reaches, and it can be reached. So I wanted to learn a little bit more about it. I've only known the kind of like hearsay about what it is, what it does, how it will affect computing, computers in general, classical computers. Will it be something that can be consumer based? Can it become something for the mass market? All these kind of things I've kind of like heard about, nothing very definitive about it. So I wanted to learn a little bit more with you guys, and hopefully, we both get to learn some stuff today. But for some reason, what was that? It just said Steve Neal just subscribed. Thought you long time subscribed. Not sure why that notification just came through. But anyways, either way, we appreciate the subscription. So I just wanted to start off with this video to kind of break us into what is quantum computing. I like these 5 levels of difficulty videos, where they break it down from a kid's perspective to teenagers to a college student to a grad student and then to an expert. I do like to see those different kind of levels because it also allows us to see the progression and get a little bit of basic understanding and then get a little bit more in depth. So I did want to watch this video today to kind of kick off the stream. But yes, guys, if you're now joining into the stream and you like what we're doing and like what we're going to be talking about, please don't hesitate to like the stream and subscribe. I'd really appreciate it. It'd mean a lot to me. We're trying to build a community here, and you guys are our primary source for that community. So I do appreciate you spending your time to listen to me talk today. But let's go ahead and kick off this video. Make sure everything is all sorted out. One second, guys. Just want to make sure I got everything sorted on my end. Interesting, it's not letting me see my subscribers. Why are you not letting me see my subscribers? Anyway, I guess I'll leave that to... Oh, there it is. Interesting. Well, alrighty, that makes a lot of sense. Okay, so let's kick it off. Let's start this video today. I hope everybody's having a good Thursday. We're almost to the weekend, guys. We're almost there. So let's kick it off. Let's learn a little stuff about quantum computing. I'm excited. I hope you guys are too.
Hi, my name's Talia Gershon, and I'm a scientist at IBM Research. Today I've been challenged to explain a topic with 5 levels of increasing complexity. It's a completely different kind of computing called quantum computing. Quantum computers approach solving problems in a fundamentally new way, and we hope that by taking this new approach to computation, we'll be able to start exploring some problems that we could never solve any other way. Hopefully by the end of today, everyone can leave this discussion understanding quantum computing at some level.
Even if it's just level 1, we'll take it.
Yeah, what do you think that is?
Fancy chandelier.
Oh,
I think so too. We jokingly call it the chandelier. That's real gold, you know. This is a quantum computer.
It's a quantum.
Wow, I didn't expect them to actually show a video, I mean, images of it or video of it. I want to go back and see that, guys,
So too.
because
We jokingly call it the chandelier.
wow, I've never seen one before. That is
It's real gold, you know. This is a quantum computer.
It's a quantum.
Yeah, it's a really special kind of computer.
What does it do?
It calculates things, but in a totally different way to how your computer calculates things. What do you think this is?
A
Yeah. You know what your computer thinks that is?
0 1.
This really specific combination of zeros and ones. Everything that your computer does, showing you Pink Panther videos on YouTube, calculating things, searching the internet, it does all of that with a really specific combination of zeros and ones, which is crazy, right? That would be like saying your computer only understands these quarters. For each quarter, you need to tell it that you're going to use heads, tails, and you assign it heads or tails. So I can switch between heads and tails, and I can switch the zeros and ones in my computer so that it represents what I want it to represent, like an A. And with quantum computers, we have new rules we get to use too. We can actually spin one of our quarters. So it doesn't have to choose just one or the other.
Can computers help you with your homework, your really hard homework?
Yeah, they can. Especially if doing your homework involves calculating something or finding information. But what if your homework was to discover something totally new? A lot of those discovery questions are much harder to solve using the computers we have today. So the reason we're building these kinds of computers is because we think that maybe one day they're going to do a lot of really important things, like help us understand nature better, maybe help us create new medicines to help people.
Well, before we get on to the teen part, I just want to point out to you guys that what she said about the zeros and ones. So all of our classical computers that we're, the computer that I'm using right now, if you're not familiar with it, everything is done in zeros and ones. That's the primary, that's the core language. It's not a set, it's machine, that is the machine language, or binary is considered machine language. Yes, I'm pretty sure. Then it's assembly, and then it goes into higher level languages. But yes, the primary language that computers almost, what they speak in and what they understand is zeros and ones. Because it kind of goes back to how circuitry works in electrical circuits, where a 0 implies that a circuit is closed and a 1 implies that it's open. So therefore, or is it the other way around? I'm pretty sure zeros is closed and ones is open. So that's why I'm pretty confident that's why they started to use binary in the beginning, zeros and ones, because it was the easiest to represent in comparison to how an electrical circuit actually works. Now, what she just said was a little bit mind-blowing, is that the basic language that all computers to this day, every computing device that performs some sort of calculations, uses zeros and ones, and a quantum computer, which is something that they're recently developing and have been in the process of developing for some time and will continue to develop for some time, no longer only uses zeros and ones. But she represented it and said that one of the coins that represented a 1 or a 0, instead of changing it to a 0 to represent something different from a 1, you can spin the coin. Which, if you understand quantum physics, kind of makes sense, because I know that quantum physics is the science of taking into every single scenario into account. For instance, if you were to go into a bar and you ordered an orange juice, you would need to take into consideration quantum physics says you would need to take into consideration every other option on the menu, because there is a probability that you may get it. If the bartender misplaces your order, doesn't understand what you said, and instead of an orange juice, he gives you an apple juice, or a beer even, and he does that, and so they have to take into all those things into account. So when she says spin the coin, it kind of sounds really similar to quantum physics in the sense that you have to take into account, could that be a 0 or could that be a 1? That's where I am right now. Remember, guys, I'm learning this with y'all. I want you to learn it with me as well. So we're going to try and take it step by step and gain our understanding. I'm going to stop in between each one of these and try and gain some understanding based off of what she's saying. And then we'll, dive into some more stuff.
What's your favorite kind of computer? Smartphone, tablet, regular, laptop, PC?
I've got to go with my iPhone.
So what do you do with your iPhone?
Social media,
That's about it.
use it for studying
Have you ever run out of space on your iPhone?
all the time.
Me too.
Yeah, always when I'm trying to take a photo.
So did you know that there's certain kinds of problems that computers sort of run out of space almost? Like you're trying to solve the problem, and just like how you run out of space on your iPhone when you're trying to take a picture, if you're trying to solve the problem, you just run out of space.
Yeah.
And even if you have the world's biggest supercomputer, did you know that can still happen?
Wow.
So my team is working on building new kinds of computers altogether, ones that operate by a totally different set of rules. So do you know what that is?
I have no clue.
It's a quantum computer.
That's incredible,
What?
guys. I'm not gonna lie.
Have you ever heard of a quantum computer?
I haven't.
Have you ever heard of the word quantum?
No.
Okay,
Really?
so
Interesting.
quantum mechanics is a branch of science, just like any other branch of science. It's a branch of physics. It's the study of things that are either really, really small, really, really well isolated, or really, really cold. And this particular branch of science is something we're using to totally reimagine how computing works. So we're building totally new kinds of computers based on the laws of quantum mechanics. That's what a quantum computer is.
Huh.
I'm going to start by
Which
telling you
is,
about something called
before she gets into that, which is really interesting that, I guess, when you're developing the first computer, you're not really taking that into account. And I don't even know if quantum physics was such a big topic when computers were being developed. I actually don't think so, because I know quantum physics is a relatively new type of science. Not relatively new, but within, I would say, past 30 years. I actually want to look that up right now real quick before we get back into it, guys. Let's actually see that. Let's see, because I wanted to know that. How old is quantum physics? That's a normal thing. Quantum mechanics was adopted in the mid-1920s. Okay, well then no then. That is, yeah, with the black body radiation problem. Yes, I remember studying that in school. Good fun. So it says it is in 1920, so it started in like 1905 with the photoelectric effect. Yeah, I remember that. Studying that too. Oh, interesting. The stuff you learn at school that you just, pops back into your memory whenever it feels like. So, yeah, so I guess, it was developed and invented or conceptualized, that science, prior to computers being, fully mass produced or whatnot. So it's interesting that, maybe they just said, okay, we're not even going to attempt to really try to head in that direction. The easier one is just to know how we work with electrical circuits, which is zeros and ones. Ones being circuit is open, zeros being the circuit is closed, and, we're just going to work in that fashion. Yes, because, guys, if you didn't know, the first computers and the first programmers had to program in zeros and ones. That was quickly changed to when we had, like, assembly language and other languages that would be then translated to zeros and ones binary. But it's interesting that this was, only like conceptualized, like, oh, we should apply this to something that we use every single day. Computers are used everywhere daily. Like, some form of computing technology, no matter if it's the oldest computer right now, is still being used in some of the most remote areas. And yet they just were like, let's just head with the easier route maybe. But let's hear what she has to say, though.
Position. So I'm going to explain it using this giant penny.
Wow.
I'm not gonna lie, guys, she got a lot of props. The last couple of videos I've been watching from this 5 levels of difficulty, they don't got any props. She's coming prepared. She came she came not only with 5 coins in the first stage, but she's come with a big penny.
100 pennies.
I don't know what it's worth, but I can put it face up, right? And that's heads. I can put it face down, right? So at any given point in time, if I ask you, is my penny heads or tails, probably you could answer it, right?
Yeah.
Okay. But what if I spin the penny? So let's do it. Okay, so while it's spinning, is it heads or tails?
Heads.
While it's spinning?
Oh, I would know.
It's sort of a combination of heads and tails, right? Would you say? So superposition is this idea that my penny is not just either heads or tails. It's in this state, which is a combination of heads and tails.
Yeah.
This quantum property is something that we can have in real physical objects in the world. So that's superposition. And the second thing that we'll talk about is called entanglement. So now I'm going to give you a penny. Wow! When we use the word entangled in everyday language, what do we mean?
That something's intertwined or...
Exactly, that there's two things that are connected in some way, and usually we can separate them again.
Yeah.
If your hair is tangled or whatever, you can unentangle it, right?
Yeah.
But in the quantum world, when we entangle things, they're really now connected. It's much, much harder to separate them again. So using the same analogy, we spin our pennies and eventually they both stop, right? And when they stop, it's either heads or tails, right? So in my case, I got tails and you got heads. You see how they're totally disconnected from each other, right? Our pennies.
Oh, come on. You know, we gotta get rid of that copyright
our
somehow.
pennies were
So we gotta
entangled,
accept the ads.
And we both spun them together.
Next time I'm gonna make
Right?
next time I'm gonna make sure to jump over this guy. Gotta move quickly.
When we stop them,
12,
if you measured
15.
your penny to be a head, I would measure my penny to be a head. And if you measured your penny to be a tails, I would measure my penny to be a tails. If we measured it at exactly the same time, we would still find that they were both exactly correlated.
That's crazy.
It's so cool, right?
Oh my god.
The way that we are able
I didn't catch
to
that.
view and we both stop, it's either heads or tails, right? So in my case, I got tails and you got heads. You see how they're totally disconnected from each other, right? Our pennies in the real world. Now, if our pennies were entangled and we both spun them together, right? When we stop them, if you measured your penny to be a head, I would measure my penny to be a head. And if you measured your penny to be a tails, I would measure my penny to be a tails. If we measured it at exactly the same time, we would still find that they were both exactly correlated.
That's crazy.
It's so cool, right?
Oh my god.
The way that we are able to actually see these quantum properties is by making our quantum chips really, really cold. So that's what this is all about, actually. This is called a dilution refrigerator, and it's a refrigerator. It doesn't look like a normal refrigerator, right? But it's something that we use. Actually, there's usually a case around it to cool our quantum chips down cold enough that we can create superpositions and we can entangle qubits, and the information isn't lost to the environment.
Like, what could those chips be used to do?
So one of the things that we're trying to use quantum computers to do is simulating chemical bonding. Use a quantum system to model a quantum system.
Yeah, I mean, I'm definitely going to impress all my friends when I tell them about this. They're going to be like, quantum what?
Oh wow.
So what do you think that thing is?
Is it some sort of conductor circuit?
That is a really good guess. There's parts of that that are definitely about conducting. This is the inside of a quantum computer.
Oh, wow.
So, pretty much what she just told me is that entire thing. That probably blew my mind the most just now. Was that I thought that part. I understand that it's quantum chips, but like I thought that the concept of it was much greater than that. That entire shell is pretty much just used to make the quantum chip be at such a sub-zero temperature, or I don't know if it's sub-zero, but so cold that they can intertwine the bits, like how we would have zeros and ones, which are separated. They are completely separated. But when they're able to cool the chip down to such a rate that they're able to intertwine the zeros and ones, you know, I need further explanation here.
Yeah, this whole infrastructure is all about creating levels that get progressively colder as you go from top to bottom down to the quantum chip, which is how we actually control.
Look at the size of it, guys. That is incredible. The way, what? Guys, and I'm gonna say that I'm assuming that this is the chip. This is just, you know, a conductor or whatnot to allow it to the cold to transfer to the chip. It's probably made of some material, probably a copper material or something like that. Actually, it looks copper, but it's probably made of something with something that's able to hold temperature at a much better rate than copper. I'm not sure if copper is high up there, but the chip is this big. That entire machine, every single one of these things are gold, actual solid gold, or not, well, solid in some cases, and maybe not solid, but made out of gold metal. And this is the little chip here that entire machine is being used
Oh, wow.
to cool.
So when you say colder, you mean like physically colder?
Yeah, like physically colder. So room temperature is 300 Kelvin. As you get down all the way to the bottom of the fridge, it's at 10 millikelvin.
Oh, wow.
Yeah. Amanda, what do you study?
So I'm studying computer science, currently a sophomore, and the track that I'm in is the intelligent systems track. Machine learning, artificial intelligence.
Have you ever heard of quantum computing?
From my understanding, with a quantum computer, rather than using transistors, is using spins. You can have superposition of spins, so different states. More combinations means more memory.
So that's pretty good. So you mentioned superposition, but you can also use other quantum properties like entanglement. Have you heard of entanglement?
I have not.
Okay, so it's this idea that you have two objects, and when you entangle them together, they become connected.
Oh, okay.
And then they're sort of permanently connected to each other, and they behave in ways that are sort of a system now. So superposition is one quantum property that we use. Entanglement is another quantum property, and a third is interference. How much do you know about interference?
Not much.
Okay, so how do noise-canceling headphones work?
They read like ambient wavelengths and then produce like the opposite one to cancel out.
They create interference. So you can have constructive interference and you can have destructive interference. If you have constructive interference, you have amplitudes, wave amplitudes that add, and so the signal gets larger. And if you have destructive interference, the amplitudes cancel. By using a property like interference, we can control quantum states and amplify the kinds of signals that are towards the right answer and then cancel the types of signals that are leading to the wrong answer. So given that you know that we're trying to use superposition, entanglement, and interference for computation, how do you think we build these computers?
I have no idea.
So step one is you need to be able to have an object or physical device, we call it a qubit or quantum bit, that can actually handle those things, can actually be put into superpositions of states. You know, two qubit states that you can physically entangle with each other. That's not really trivial, right? Things in our classical world, you can't really entangle things in our classical world so easily. We need to use devices where they can support a quantum state and we can manipulate that quantum state. Atoms, ions, and in our case, superconducting qubits. We make qubits out of superconducting materials.
But as like a programmer, how would quantum computing affect a different way of writing a program?
It's a perfect question. I mean, it's very early for quantum computing, but we're building assembly languages. We're building layers of abstraction that are going to get you to a point as a programmer
To do
where
high-level
you can
programming.
interchangeably be programming something the way that you already do and then make calls to a quantum computer so that you can bring it in when it makes sense. We're not envisioning quantum computers completely replacing classical computers anytime soon. We think that quantum computing is going to be used to accelerate the kinds of things that are really hard for classical machines.
So what exactly are some of those problems?
Simulating nature is something that's really hard because if you take something like, modeling atomic bonding and electronic orbital overlap, instead of now writing out a giant summation over many terms, you try and actually mimic the system you're trying to simulate directly on a quantum computer, which we can do for chemistry. And we're looking at ways of doing that for other types of things. There's a lot of exciting research right now on machine learning, trying to use quantum systems to accelerate machine learning problems.
So would it be like in 5 years or 10 years that I would be able to have like one of these sitting
I would
in
say 20
my
years.
laptop just in my dorm?
I don't think you're going to have one in your dorm room anytime soon, but you'll have access to one. There's 3 free quantum computers that are all sitting in this lab here that anyone in the world can access through the cloud.
Okay, so quantum computing creates new possibilities and new ways to approach problems that classical computers have difficulty doing.
Couldn't have said it better myself.
Even when
So
she
I'm,
breaks
first-
it down like that, it is still very difficult for me to wrap my head around. So, I think they miss out a lot of information. It's like, right now, before I even want to hear what this guy has to say, I kind of want to know what is a qubit. Like, I understand that they're using conductors to semiconducting materials to create qubits, but she wasn't very specific about what is a qubit. What is a qubit? Is that what it is? Qubit. I don't know. Is it qubit for quantum? It's with a Q. Makes sense. Makes sense that a qubit is with a Q. A qubit is a quantum bit. The counterpart is in quantum computing to the binary digit or bit of classical computing. So instead of having a binary digit, which is so that's a binary bit, which is 1 or 0. A qubit is their name for their bit. Their version of the 1s and 0s. Come on with the ads, man. A qubit is a quantum bit. The counter bit part in quantum computing? Yes. A qubit is the basic unit of information in a quantum computer. So it's pretty much just replacing normal bits with quantum bits. So they call it qubits. So, in a quantum computer, a number of elemental particles, such as electrons or photons, we're electrons, can be used. In practice, success has only been achieved with ions. Okay, so with ions, they're currently having success with ions, with either their charge or polarization acting as a representation of a 0 or a 1, which makes sense because with atoms, you have well, you can have more than +1 or -1, but usually each photon, a neutron is 0, an electron is 1, and a proton is -1, I think. So I guess they're only that variation by 1, so that makes sense. Each of these particles is known as a qubit. So it's pretty much representing the particle. So the ion that they're currently using, because they said that they've only been had success with ions. So the ion that they're using is as represented as either 0 or 1, which makes sense because an ion could both be positively or negatively charged, or neutral. I'm pretty sure. I'm not a I'm a chemistry major, but that's my memory based off of what I took in school when I was 16. So, geez, almost 9 years ago. Wow. No, sorry, no, almost 7 years ago. Well, I'm crazy now. Or 8 years. No. Yeah, almost 8 years ago. Wow. Guess I can't do math. But, yes. So, they're using these ions as a qubit, the nature of behavior of these particles. So they're pretty much using a particle to represent a bit. An ion is the bit. Instead of like an electrical component where it's a 0 or a 1, they're using an ion to replace that transistor that's doing the 0 and the 1. It's kind of where I'm at right now. That makes sense. So she said the most relevant aspects are the superposition, entanglement, and interference. So the superposition makes sense. That's where, okay, think of it, a qubit as an electron in a magnetic field. So electron is circling in a magnetic field, is following the magnetic field lines, right? The electron spin may be either in alignment with the field, which is known as spin up state, or opposite to the field, which is known as spin down state. Changing the electron spin from one state to the other is achieved by using a pulse of energy, such as a laser. Let's say that we use 1 unit of laser energy, but if we only use half a unit of laser energy and completely isolate the particle from all external influences, what if we only use half a unit of laser energy and completely isolate the particle from all external influences? According to quantum law, the particle has then either enters a superposition of states where it can be either going to spin down or the spin up. So it's in that in between state. In which it believes as if it were in both states simultaneously. Okay, so that's where the spinning of the coin that she was showing us is that it's technically can be quantified as being in both states at the same time, because technically they're undecided. So they are using that principle of superposition to get the ion in that state where it is neither a 0 or a 1, but both at the same time. A little confusing. Yes, or not a little confusing, a lot of confusing. Yes, guys, this is definitely a very intense topic, but I am diving in head first right now. So, thus the number of computations that a quantum computer could undertake is 2 to the power of n, where n is the number of qubits. Makes sense. A quantum computer comprised of 500 qubits would have a potential to do 200 to the power of 2 to the power of 500 calculations in a single step, which is a very big number. That is, wow. Is more atoms than they are in the known universe. Yes, guys, if you know what 2 to the power of 500 is, pretty much 2 by 2 by 2 by 2 by 2 all the way to 500. That is a massive number, and they clearly have proven that by saying that that is more numbers than they are atoms in the entire known universe. Wow. Classical computers today, even with so-called parallel processors, still can only do one thing at a time. There are just 2 or more of them doing it. But how will particles interact with each other? They do so via quantum entanglement. So, classical computers, we have parallel processors which can appear to run tasks simultaneously, when in truth they're taking turns to appear like if they're running at the same time, but they can only do one thing at a time. So they're trying to use quantum computing to kind of replace that, where we no longer have to rely on taking turns in a very intelligent and organized manner, where they are making sure that they're getting the most they're being the most productive. That's how normal classical computers pretty much operate with parallel processing. They want to be as productive as possible and processing in a parallel pattern, So they're processing a task, they're doing tasks almost at the same time, but they're really not, because they're interchanging with each other. this task runs, it stops, this task starts, stop, stop, start, stop, start, stop, start, until they both reach completion, and they're doing it in such a manner that they're not wasting any time on one task. They are multitasking in a sense. But they're at no point doing both things at the same exact time, so they're trying to use quantum computers to make it so that they can do those two things at the same time? Maybe. Okay. So, how would these particles interact with each other? They would do so via quantum entanglement. So, they got the ions already. The ions are in a superposition state where they're neither in a spin down or a spin up state. They are neither a 0 or a 1, but both. So, they got that part there. Now, so they have one ion like that, and now they're getting the next ion and doing the same thing. But how do they get these ions to now correlate and work with each other? So, particles that have interacted at some point retain a type of connection and can be entangled with each other in pairs, in a process known as correlations. Particles that have been interacted at some point retain a type of connection. That is interesting. I did not know that. So I guess if any particle has interacted with another particle, they pretty much have some sort of underlying connection because of their once interaction. So knowing the spin state of one entangled particle up or down allows one to know the spin state of its mate in the opposite direction. Wow. So they're pretty much saying in one of the entangled particles, if they know that the spin state is either up or down, it allows them to know what its other entangled particle state is in the opposite direction. Even more amazing is the knowledge that due to the phenomenon of superposition, the measured particle has no single spin direction before being measured. The measured particle has no single spin direction before measuring, but is simultaneously in both a spin up and a spin down state. Yeah. The spin state of a particle being measured is decided at the time of measurement and communicated to the correlated particle. So they measured at the same time, which simultaneously assumes the opposite spin direction to that of the measured particle. This is a real phenomenon. Einstein called it spooky action at a distance. Wow, I did not know that. The mechanism of which cannot as yet be explained by any theory. So that is, I'm just going to stop right there and say they're applying something that can't be explained. Interesting. Nice. That is, I guess, guys, going to be the main part of the hardest part to jump over in this talk today, is because they pretty much haven't proven they can't explain superpositioning, which is how we can determine that something could be in the in-between state of something, neither one thing or the other, but both, because they technically haven't chosen. It's almost like, you know, spinning the coin. It hasn't chosen to fall on a side yet, or, well, it hasn't chosen. It hasn't fallen on a side yet, so it hasn't made that decision. But, so they can't explain that theory, and yet they're applying it to quantum computers. That is a little interesting. Quantum entanglement allows qubits that are separated by an incredible distances to interact with each other. Now, guys, when they say incredible distances, I am not sure what they mean. Are they referring to severe distance, like actual, like from a satellite to Earth? If so, that's really intense. I don't know if that's true. Could it possibly be just that because it's so small that they seem like really big distances from each other than normal? We'll find out in a little bit. So no matter how great the distance between the correlated particles, they will remain entangled as long as they are isolated. What? If it is in fact that it's not limited to the speed of light, so I'm assuming, guys, that definitely means when they say large distances, they mean large distances, not like from here, not like in a small atom and they're just separated by something so small, but to them it is very large. They're actually saying to us it's large, so like to the moon and on Earth, or in a satellite to Earth, which is I actually had spoken to my boss earlier, and he mentioned something about them doing a study with a 1,000 kilometer distance, and the speed at which the particles interacted with each other was faster than the speed of light. Much faster than the speed of light. So that is crazy. That they're connected. Guys, remember what they just said, that the entanglement, once they've interacted with each other, so if they take two ions, which are now qubits, and they have the qubits entangled, and the qubits have interacted with each other, they can be separated but still entangled. So one could be in a space station, and the other one could be on Earth. And yet, they can communicate, or they can measure the opposite of one to the other. So they can use wherever they are to measure the state of the other particle, but in an opposite direction. Okay, so I'm getting a little, I'm grasping a little bit here, but I think I'm getting it a little bit. So no matter how great the distance between the correlated particles, they will remain entangled as long as they are isolated. So I'm assuming they have to keep them in a very cold environment. I'm thinking that's where they coming at, where our expert lady here was explaining to us that they have to keep them very cold. So that's probably the isolated environment that she's referring to, is that they need to be freezing and they need to be kept in that freezing environment and stable. So taken together, quantum superposition and entanglement create an enormously enhanced computing power, where a 2-bit register in an ordinary computer can only store 4-bit configurations. Makes sense? Guys, remember, our computers are both, our operating systems are either 32-bit or 64-bit. That's what they're kind of reaching at. When you have a 32-bit or a 64-bit, you have much more combinations or configurations. If it's just a 2-bit, then you only have 4 configurations: 00, 01, 10, and 11. So that makes sense. So if, let me see if I can write that down for you. So if you have a 16-bit, then that is going to be, that would be what, 2 to the 4 combinations, right? Wow. So 2 by 2, I can't do math. So no, 2 to the 3. So 2 to the 3. So that's how many combinations? That'll be 2 to the 2 by 3 combinations, or be 30. So 2-bit, 16-bit. What? That would be 32 configurations. All right, I'm not gonna get lost in the math here. At any given time, in a 2-qubit register in a quantum computer can store all 4 numbers simultaneously, because each qubit represents 2 values. If more qubits are added, the increased capacity is expanded exponentially. Okay, so what she's saying, or what this is saying, is that when you have, instead of a 2-bit register where you have 4 combinations or binary configurations, in a 2-qubit register, you have, it can store 4 of these combinations at the same time. So it never has to jump in between these configurations. It's never going to be just a 00 or a 01 or a 10 or a 11. It is all 4 at the same time, because each of the qubits represent 2 values. Alrighty. I think I'm a little bit closer, guys. I'm hoping you guys are a little bit closer too.
I'm a master's student, and I'm studying machine learning. So it's in the computer science department, but it mixes computer science with math and probability and statistics.
So have you come up upon sort of any limits to machine learning?
Certainly, depending on the complexity of your model, then computational speed is one thing.
I have colleagues here that tell me it can take up to weeks to train certain neural networks, right?
Sure, yeah.
And actually, machine learning is one research direction where we're really hoping that we're going to find key parts of the machine learning computation that can be sped up using quantum computing.
Yeah, it's exciting. So in a classical computer, you have all sorts of logical gates that perform operations, and they change an input to some sort of output. But I guess it's not immediately obvious how you do that with quantum computers.
If you think about even just classical information like bits, right? At the end of the day, when you store a bit in your hard drive, there's a magnetic domain and you have a magnetic polarization, right?
Sure.
You can change the magnetization to be pointing up or pointing down, right? Quantum systems, we're still manipulating a device and changing the quantum state of that device. You can imagine if it's a spin, that you could have spin up and spin down, but you can also, if you isolate it enough, you can have a superposition of up and down.
Sure.
So what we do when we try to solve problems with a quantum computer is we encode parts of the problem we're trying to solve into a complex quantum state. And then we manipulate that state to drive it towards what will eventually represent the solution.
So how do we actually encode it to start with?
Yeah, that's a really good question. This actually is a model of the
Focus.
I missed it, guys.
You commit to it, it will come true.
inside of one of our quantum computers.
Okay.
So you need a chip with qubits. Each qubit is a carrier of quantum information, and the way we control the state of that qubit is using microwave pulses. You send them all the way down these cables, and we've calibrated these microwave pulses so that we know exactly this kind of pulse with this frequency and this duration will put the qubit into superposition, or will flip the state of the qubit from 0 to 1. Or if we apply a microwave pulse between two qubits, we can entangle them.
How do we measure
Yes, exactly, also through microwave signals.
Okay.
The key is to come up with algorithms where the result is deterministic.
Interesting. So what do those algorithms look like?
There's sort of two main classes of quantum algorithms. There's algorithms which were developed for decades, right? Things like Shor's algorithm, which is for factoring, Grover's algorithm for unstructured search, and these algorithms were designed assuming that you had a perfect fault-tolerant quantum computer, which is many decades away. So we're currently in a phase where we're exploring what can we do with these near-term quantum computers. And the answer is going to be, well, we need different kinds of algorithms to really even explore that question.
Yeah, certainly having a search algorithm is very useful. Factoring, those are definitely useful things that I would imagine could be done a lot faster on a quantum computer.
Yeah. They also, unfortunately, require fault tolerance. Right now, the algorithms that we know of today to do those things on a quantum computer require you to have millions of error-corrected qubits. Today we're at like 50, and it's actually amazing that we're at 50. There's things that we know or we have strong reason to believe are going to be faster to do on a quantum computer. And then there's things that we'll discover just by virtue of having one.
Sure. How could someone like me who's a grad student get involved in this, or what kinds of challenges are you facing that someone like me could help out with?
I'm glad you're interested. I think the place where lots of people can get involved right now is by going and trying it out and thinking about what they could do with it. There's a lot of opportunity to find these near-term applications that are only going to be found by trying things out.
I'm a theorist.
You know, I don't know why it feels like they're just skimming the surface for me. I would like for these videos to be longer, to really give me a little bit more in-depth conversation, because I know they do a lot of editing for these videos, and I would love for if they didn't do all the editing so that I can get every question, because I'm sure that guy asked quite a few more questions. He seemed like he was very interested. If I was there, I would have been drilling them with questions.
Theoretical physicist. I started out in condensed matter theory, the theory that studies superconductors and magnets, and I had to learn a new field of quantum optics and apply those ideas. One of the nice things about being a theorist is you get to keep learning new things.
So Steve, tell me about your research and the work you've been doing in quantum computing.
My main focus right now is quantum error correction and trying to understand this concept of fault tolerance, which everybody thinks they know it when they see it, but nobody in the quantum case can precisely define it.
It's something that we've already figured out for classical computing. Like, something that amazes me is all the parallels between what we're going through now for quantum computing and what we went through for classical computing.
I was asking a computer scientist recently where to read about fault tolerance in classical computing. He said, oh, they don't teach that in computer science classes anymore because the hardware has become so reliable. In a quantum system, when you look at it or make measurements, it can change in a way that's beyond your control. We have the following task: build a nearly perfect computer out of a whole bunch of imperfect parts.
Common myth. How many qubits do you have? That's the only thing that matters. Or just add more qubits. What's the big deal? Pattern them on your chip.
The great power of a quantum computer is also its Achilles heel, that it's very, very sensitive to perturbations and noise and environmental effects.
Wow.
You're just multiplying your problems if all you're doing is adding qubits.
Exactly. So I think something that frustrates a lot of people about quantum computing is the concept of decoherence, right? You can only keep your information quantum for so long, right? And that limits how many operations you can do in a row before you lose your information.
That's the challenge, I would say. As much progress as we've made, it's a frustration to still be facing it.
Let's talk about some of the things we think need to happen between now and fully fault-tolerant quantum computers to get us to that reality. I mean, there's so many things that need to happen. In my mind, one of the things we need to do is build all these different layers of abstraction that make it easier for programmers to come in and just enter at the ground level, you know?
Yeah, exactly. So I think there's going to be a kind of...
So before you, I like how they're kind of, you know, it's interesting, you know, you always say that testing something is what improves it. You know, they had classical computers, and in order to make them what they are reliable as they are today, you had to test them. You had to do the necessary tests. You had to attempt to break them almost. You had to try and break something and then figure out how to prevent you from being able to do that break again. And that was the whole process. And it's funny how she's pretty much, when she said that, it's interesting how we're the same issues that they went through when they were developing a computer, or classical computers, is the same issues that they're entering now, they're dealing with now when they're developing quantum computers. Which, you know, and she's hitting the same nail on the head, that they need more people to be interested in it, to try and play around with the machines to learn more about the machine. Because as she's saying, and as he was saying, this gentleman here, that because so many things in a quantum computer can change, and without your expecting it to change, that you need to do as much to register those change. You have to keep using it in the same sort of manner to figure out what is resulting in this change, or what causes this change, and how to combat that change, I think, is where they're kind of hitting at. So it's very interesting how, you know, they're pretty much rewriting the process of building a computer, in a sense. It is no longer, yeah, we have classical computers, and she said, and when the undergrad had mentioned, would I be having this in like 5 to 10 years? And it's a very hard thing to conceptualize, because they're pretty much starting from the ground. They have a lot of, you know, we have a lot of expertise when it comes to tech, like hardware and stuff like that. So they may, you know, they have experience working with chips and working with the same convection, pretty much the refrigerator unit that they're using right now to cool this quantum computing. So we have that experience, but we're pretty much starting from recreating the computer from scratch, a quantum computer from scratch. That's what they're pretty much doing. So we have all this advancements, but it's really not giving us that edge. But I think what's very cool about that is that when they had classical computing, there was no edge. It was really and truly the need to figure it out, the need to keep breaking it and improving it, keep breaking it and improving it. How can we fix this? How can we make this better? How can we compensate for the issues that we didn't expect? Which is what quantum computing, what he's saying the issue is how can they change it so random and haphazardly that you need to understand how to predict those issues, or to correct those faults. That's what I'm pretty much taking away. That it's just really interesting to know that it's like almost starting from scratch again. And I would like to see when they develop this, because building a computer wasn't done in a day. It was done in a long period of time, and getting to where we are now has been over the course of 30 years for us to have a computer that's a chip and hit this that is the same power of this outpasses anything from the past in this size. To get something this small is incredible. So it took time to get here. So I could only imagine when we're already here, and they're trying to change how this works, how these smartphones, how your computers, how everything that has a processing chip in here, how processors, how they work completely, and revamping it and starting it from scratch is a very difficult task, and really hard to wrap my head around as to why, you know, what would have driven them to do this. But I guess it's the hardware limitations that she keeps repeating, is that we don't have the hardware to do it, as in it's so sensitive that there's no way to really sustain it. So let's see what he has to say.
Co-evolution of the hardware and the software up here, and the sort of middleware and the whole stack.
Another common myth. In the next 5 years, quantum computing will solve climate change, cancer, right?
Right. In the next 5 years, there'll be tremendous progress in the field, but people really have to understand that we're either at the vacuum tube or transistor stage. We're trying to invent the integrated circuit and scale up. It's still very, very, very early in the development of the field.
One last myth I think we should bust, Steve. Quantum computers are on the verge of breaking into your bank account and breaking encryption and cryptography.
There does exist an algorithm, Shor's algorithm, which has been proven mathematically that if you had a large enough quantum computer, you could find the prime factors of large numbers, the basis of the RSA encryption. It's the most commonly used thing on the internet. First, we're far away from being able to
Apply
have
that.
a quantum computer big enough to execute Shor's algorithm on that scale. Second, there are plenty of other encryption schemes that don't use factoring, and I don't think anybody has to be concerned at the moment. And in the end, quantum mechanics goes to the side of privacy enhancement. If you have a quantum communication channel, you can encode information and send it through there, and it's provably secure based on the laws of physics.
You know, now that everybody around the world can access a quantum computer through the cloud, people are doing all kinds of cool things. They're building games. We've seen the emergence of quantum games, right? What do you think people want to do with them?
I have no idea what people are going to end up using them for. I mean, if you had gone back 30 years and handed somebody an iPhone, they would have called you a wizard. So
It's funny how I literally just said that. You just can't foresee this because it's pretty much putting people in a we're in a time frame where we understand technology. Well, we don't necessarily all of us understand technology, but it's in front of us. It's in our face. So we know that it exists. We can conceptualize it, we can imagine it, we can see, we can think of what the things it can do, what the things it should do, and obviously we can think of the things it shouldn't do. So we're at that point, so it's almost like we're expecting quantum computing to get here faster because of that. But the truth is, 30 years from now is probably the time that we'll have a quantum computer that's like he said, that's at the point where if we went 30 years to this point, if we went 30 years from now, and we had that quantum computer and we took it and gave it to us right now, we would consider ourselves that person to be a wizard, because it's unfathomable. The process and the time that's going to take into actually making these things a reality, as I'm seeing, just to understand it is incredible. So, and the fact that they have to be this isolated, and you know, like everything has to be very specific because of it. You know, like I guess when they were making transistors and they were using vacuum tubes, yes, they had that environment that was, you know, very strict environments. But now we no longer need that to be in an environment that's very strict. I can open up my computer right here, my processor's right there. I can, you know, it doesn't need to be in a vacuum to operate. But these guys are in that stage, so it's hard for them to, you know, really hit the ball rolling. I think, you know, it's not as easy as to just say add, as she said, add more qubits. No, because if you at the time just added more transistors to a circuit or a circuit board or whatever, where the computers are just added more, you were causing more problems because the hardware itself couldn't sustain that. And it's the same situation here. So they have to do it in such a way that they're, as he said, they're evolutionizing. Sorry, the hardware is evolving, and the hardware needs to evolve at the same rate that they're evolving the quantum aspects of quantum computing, or as they're advancing the chip itself. It's more than just advancing the quantum chip. It's advancing all the hardware around it that makes it doable. But that is pretty much the end of that video. So, and I have a bunch of questions, and I would like to learn a little bit more. So, let's look up a couple more videos so that we learn about what is a qubit. So, let's look up some stuff with more quantum computers. So, quantum computing explained. We want to see some more.
Hey, Daryl.
Hey.
Hey, how much would you pay for something you don't want?
Nothing. Is this a test?
No. Do you like getting stuff you like for free?
Yes, this feels
You
like
know,
a
everybody complains about ads, right? And I like to complain about them too, but the beauty of it, I'd rather have the ads than pay for YouTube.
It's not.
Get 6 months
YouTube
free
is
Apple
just
Music on the
a
network
vast
you
source
deserve.
of
Now buy
video
one of our
information.
best
I love it.
phones and get one on us.
For most of our history, human technology consisted of our brains, fire, and sharp sticks. While fire and sharp sticks became power plants and nuclear weapons, the biggest upgrade has happened to our brains. Since the 1960s, the power of our brain machines has kept growing exponentially, allowing computers to get smaller and more powerful at the same time. But this process is about to meet its physical limits. Computer parts are approaching the size of an atom. To understand why this is a problem, we have to clear up some basics.
Oh wow. I didn't really know that was what's forcing quantum computing, is that we've reached a point where our hardware is so small that we can't get any smaller. That is Makes a lot of sense why they're kind of forcing us here, because now we're out of limitations for our hardware, when before it was more limitations of software, I would believe. We're now at the point where we just want to keep going with software, but we don't have the hardware to do it. So that's pretty cool. I didn't really realize that.
A computer is made up of very simple components doing very simple things, representing data, the means of processing it, and control mechanisms. Computer chips contain modules, which contain logic gates, which contain transistors. A transistor is the simplest form of a data processor in computers, basically a switch that can either block or open the way for information coming through.
Remember guys, this is where that zeros and ones come into play.
This information is made up of bits, which can be set to either 0 or 1. Combinations of several bits are used to represent more complex information. Transistors are combined to create logic gates, which still do very simple stuff. For example, an AND gate sends an output of 1 if all of its inputs are 1, and an output of 0 otherwise. Combinations of logic gates finally form meaningful modules, say for adding two numbers. Once you can add, you can also multiply, and once you can multiply, you can basically do anything. Since all basic operations are literally simpler than first-grade math, you can imagine a computer as a group of 7-year-olds answering really basic math questions. A large enough bunch of them could compute anything from astrophysics to Zelda. However, with parts getting tinier and tinier, quantum physics are making things tricky. In a nutshell, a transistor is just an electric switch. Electricity is electrons moving from one place to another, so a switch is a passage that can block electrons from moving in one direction. Today, a typical scale for transistors is 40 nanometers, which is about 8 times less than the HIV virus's diameter and 500 times smaller than a red blood cell's. As transistors are shrinking to the size of only a few atoms, electrons may just transfer themselves to the other side of a blocked passage via a process called quantum tunneling. In the quantum realm, physics works quite differently from the predictable ways we're used to, and traditional computers just stop making sense. We are approaching a real physical barrier for our technological progress.
Oh wow.
To solve this problem, scientists are trying to use these unusual quantum properties to their advantage by building quantum computers. In normal computers, bits are the smallest units of information. Quantum computers use qubits, which can also be set to one of two values. A qubit can be any two-level quantum system, such as a spin in a magnetic field or a single photon. 0 and 1 are this system's possible states, like the photon's horizontal or vertical polarization. In the quantum world, the qubit doesn't have to be in just one of those, it can be in any proportions of both states at once. This is called superposition.
Yep.
But as soon as you test its value, say by sending the photon through a filter, it has to decide to be either vertically or horizontally polarized. So as long as it's unobserved, the qubit is in a superposition of probabilities for 0 and 1, and you can't predict which it will be. But the instant you measure it, it collapses into one of the definite states. Superposition is a game changer. 4 classical bits can be in one of 2 to the power of 4 different configurations at a time. That's 16 possible combinations, out of which you can use just one. 4 qubits in superposition, however, can be in all of those 16 combinations at once. This number grows exponentially with each extra qubit. 20 of them can already store 1,000,000 values in parallel.
Wow.
A really weird and unintuitive property qubits can have is entanglement, a close connection that makes each of the qubits react to a change in the other's state instantaneously, no matter how far they are apart. This means that when measuring just one entangled qubit, you can directly deduce properties of its partners without having to look. Qubit manipulation is a mind-bender as well. A normal logic gate gets a simple set of inputs and produces one definite output. A quantum gate manipulates an input of superpositions, rotates probabilities, and produces another superposition as its output. So a quantum computer sets up some qubits, applies quantum gates to entangle them and manipulate probabilities, and finally measures the outcome, collapsing superpositions to an actual sequence of zeros and ones. What this means is that you get the entire lot of calculations that are possible with your setup all done at the same time. Ultimately, you can only measure one of the results, and it will only probably be the one you want, so you may have to double check and try again. But by cleverly exploiting superposition and entanglement, this can be exponentially more efficient than would ever be possible on a normal computer. So while quantum computers will probably not replace our home computers, in some areas they are vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries.
Oh, this is exactly what I was just about to bring up. Is that she mentioned that quantum computers will not need to test every single option, and that is pretty much what he's going to talk about here with databases. When you search anything, you know, they talked about factor algorithms and also on random. I can't remember what the name of it was. Like, it was a random sort, an unsorted list or something like that, which is you don't know what's in it, so you have to sort that list. Now, in order to sort that list properly using normal computers, you'd actually have to go through each member of the list, and using some sort of sort method, you know, whether or not it be alphabetical, numerical, and increasing, decreasing, some sort of way, you need to grab that information and start to sort it in that manner. But in order to do so, you need to know all the details. You can't just start sorting something from the beginning. You technically do start from the beginning, but you need to start from the beginning and go through all possibilities. You need to check if you're sorting numbers. So let's say you have a list of numbers and you have 5, 1, 3, 4, and 2. So you start at a normal computer will start at 5. It will then, okay, if we're sorting in numerical increasing order, so we want to get this number to say 1, 2, 3, 4, 5 instead of 5, 1, 3, 4, 2. So a normal computer is going to take that 5. It's going to compare the first 5 to the second one. It's going to say, okay, the 5 is smaller. Sorry, the 5 is smaller. The 5 is bigger than the 1, and we want the 1 to be. We want to go from smallest to biggest, so it will swap that position. So it gets to 1. So now the 1 has the position of the 5. That doesn't stop though. The 5 then has to compare to the next digit, which is the 3. So the 5 compares to the 3 and realizes it is smaller, that is bigger than the 3, swaps position. So now we have 1, 3, 5. The 5 then checks with the 4 and realizes that it is bigger than the 4, so it swaps with that, and now we have 1, 3, 4, 5. The 5 checks the 2, realizes that it's smaller than that, realizes it's bigger than that, and swaps with the 2. So now we have 1, 3, 2, 5. That's not done there because obviously that's not sorted. So then the algorithm, the computer will then have to, it's going to take the 1 and confirm that the 1, the first digit, it goes back to the first digit. The 1 is now the new first digit. It's going to compare that with all the other ones. 1 with the 3, smaller than 3, fine, stays there. 1 with the 4, smaller than the 4, stays there. 1 with the 2, smaller than the 2, 1 smaller than the 5, the 1 is going to stay there. It's now going to go with the 3. The 3 checks the 4. 3 is smaller than 4, it's going to stay there. 3 checks the 2, it realizes that it is smaller than the 2, so it swaps to the 2. So now you have 1, 2, 4, 3, 5. Alright, I hope you guys are following. So now we have the 1 and the 2. So after once it makes a swap, it has to go back to the first digit and guarantee to check. This is what normal computers have to do, and they just do it at a very fast rate. That's why it appears like it's not really happening that fast, that slowly, but it really is happening slowly if you break it down. So then it checks the 1 again. Well, most computers at that point, it has sealed that the 1 is the smallest, so the 1 it will not check. The 2 then, since it's made that swap, it's going to check the 2 with the 4. 2 is smaller than a 4, okay, we're good, we're going to stay there. 2 is smaller than the 3, okay, we're good. 2 is smaller than the 5, okay, we're good. So now we're at 1, 2, 4, 3, 5. Now we're going to move to the indexing increases, guys. It starts from 0, 1, 2, 3, 4. 0 is going to be the first digit. You always start at 0. So we're now at the second index, technically the third digit, because 0, 1, 2, 3. So we're going to check the 4. So we're at 1, 2, 4, 3, 5. The 4 checks with the 3, realizes it is smaller. Sorry, it is bigger than the 4, than the 3. Oh, the 4 checks with the 3, realizes it is bigger than the 3, and it swaps. So now we have 1, 2, 3, 4, 5. Now, that doesn't mean that the computer knows that it has done. In a perfect world, the computer, you can see that it's now been sorted, but a computer doesn't know that until it has checked every possibility. That's what it is programmed to do. So now it has made the swap, so it's going to go to the third index, the 3, and confirm that the 3 is smaller than the 4, the 3 is smaller than the 5. Confirms that. Now it moves over to the third index, which is the number 4, or the 4th slot. It checks the 4 is less than the 5, true. So it doesn't do a swap. The 5 is the last digit, it moves the index, there is no more to check, and it is sealed. So that's how a normal computer does it. That is just to sort 5 numbers, and it took me so long to explain that one to you. And I had to pretty much, I have some chicken scratch here, but yeah, I had to break it down like that. So it had to go through, let me show you guys. I went through 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 steps, but the computer is going to do more than that because it has to do every single thing that I just spoke about. Now, in a quantum computing, they're saying that they won't have to do that. You wouldn't have to search for every single possibility. Now, I want them to explain why, because that's the hardest thing for me to really wrap my head around, is how do you not have to check every single option in a database to make sure that you are sorting it correctly or you are finding the correct result. You know, if you're searching a database for the number 5 and we have these 5 numbers, it's going to have to check the first digit, the second digit, the third digit, the fourth digit, and the fifth digit. And after we've sorted it, the fifth is in the last place, so it looks for the 5. Done. Now, let's see how quantum computer is going to get that part done, because I'm fascinated to know about that.
Vastly superior. One of them is database searching. To find something in a database, a normal computer may have to test every single one of its entries. Quantum algorithms need only the square root of that time, which for large databases is a huge difference. The most famous use of quantum computers is ruining IT security. Right now, your browsing, email and banking data is being kept secure by an encryption system in which you give everyone a public key to encode messages only you can decode. The problem is that this public key can actually be used to calculate your secret private key. Luckily, doing the necessary math on any normal computer would literally take years of trial and error. But a quantum computer with exponential speedup could do it in a breeze.
Okay, so they didn't explain what I wanted to hear about the database, so that's the next thing I'm going to look for as soon as this finishes. But he is going into the whole part about what the last guy spoke about, the physicist, the expert, in the last video that we watched, where he where he mentioned that quantum people are always worried that, you know, once quantum computers come out, we're not going to have any safety password, everybody's going to be able to hack everybody. Yes, in that form, if you're using that kind of encryption, then okay, it makes sense, because there is an algorithm that can decode encryptions, because most encryptions are based off of prime factors. And if you can use quantum computers to find those prime factors of very large numbers, which would take a normal computer very long to do, and would be pointless, because it would, you know, at a certain rate encryptions change so that they won't have the time to do so. A quantum computer could get it done in the time frame that it needs to. But not all computers are encrypted using prime factors, so yeah, don't let it scare you with what he's about to say, because that last expert pretty much debunked that whole myth. Because at that time, we'll just change how we encrypt things. And that's not to say that quantum computers won't change to then figure out those encryptions, but that's the point of people studying network security, is that's their goal, is to keep things encrypted and to keep things secure. So we should know that as we progress with all technology, guys, there are other people that are also counteracting whatever negative aspects happen with this with technology. You know, that is something that's more recent in our era, that people, you know, when things are developed that may affect other things that are done a certain way, they compensate for that and they make the necessary changes to prevent that from happening. But of course, when computers were first launched and the internet was first let out to the public, there were a lot of exposures, a lot of issues, a lot of loopholes, a lot of ins and ways, and pretty much exploitations for most things on the internet. And, you know, we had to grow past that. So it is not a difficult, I guess, now that everything is on, that a lot of people's information is on their computers, and we rely on computers for holding a lot of our information, our banking information, our money, everything, that it's a little bit more worrisome to think, okay, if now we get to that leap, we make that leap from classical computers to quantum computers, and people start to exploit quantum computers' ability to interfere with everything that we've been using, the system that we've been using already, then yes, it could be, you know, a little worrisome, but we got to realize that they're going to put the necessary steps in place to prevent that from happening. Not right now, there's not going to have a person, well, I can't say that for guarantee, but there's less very low chances that there's someone in a warehouse right now by themselves or the team without a huge amount of funding building a quantum computer to do exactly that. They would have to be, you know, pretty much getting a large amount of funding and with lower expectations, because it isn't a guarantee that they're going to get it done. They haven't been completed yet. It'll be different than if someone has completed a quantum computer and then had a and then yes, you know, they have people trying to recreate those quantum computers. Makes sense. They're using data that exists or can be found through the cloud. You know, she just explained, our last expert pretty much just explained that you can access this computer in the cloud. And if they are able to do so, they'll be able to get information. I'm not sure at the point if they actually finished it, if they would let them get that information. But if so, then yeah, it's understandable to believe there's probably people that want to do bad things are going to try and create their own own quantum computers. But in reality, right now they can't, because there isn't one that's fully functional. There isn't one that is completed in the sense that it is done. Here we go. This is the first iteration of quantum computers. This is what the basis of us to then start to evolve. Not where they're at right now, where they're not satisfied, when they know that it can't do the things that they want to really do. And when they reach that point, yes, we can cross that bridge then. But I'm confident that they will be putting the necessary things in place to prevent any of these, you know, decryption algorithms from being used for quantum computers. We're very far from this, guys, and you know, networking security and even just security in general is increasing drastically. You know, when we first started using computers and computers became household objects and everybody had them in their homes and everybody was relying on them, there was extreme weaknesses in that, and that people would be able to, you know, access people's information wrongfully and etc. And you know, we don't want the list goes on and on for the security risks. But those things are not as readily, you know, in existence now. If you educate yourself, if you get the necessary equipment, WatchGuard security, we recommend that heavily to secure your network. You know, antiviruses, and even, you know, using virtual private networks to protect your identity. All of those things are now where we're at now, and those are constantly evolving. And it had to take that time. We had to go through the process of having computers, realizing the weaknesses that they had for having a network of computers or having, you know, an internet. We had to look at the weaknesses, we had to acknowledge the weaknesses to then combat them. So to say that, you know, if we invent quantum computers, it's over, we're gonna just, everything we have is gonna be at risk, blah blah blah, it's not really true, because we're gonna do it in such a way that we're gonna be forced to counteract those issues. We're going to be forced to counteract whatever it is that a quantum computer can do that we may not want it to do. You know, because guys, believe it or not, everything that could do good, most of the time people can find a way to do bad with. It's just human nature almost. It's sad, but it's the truth. So let's finish it up. I just wanted to, you know, kind of take a little bit of a slow explanation for that one. I just want to kind of clear the air on that, so that people that are pretty worried about if we have quantum computers, it'll change everything and nothing will be the same, that my information will be secure. And that's not true, guys. We accelerate things. Things are pretty much proportional. As technology increases, we are proportionally, we're directly proportional to the increase in counteracting the negative effects of technology, if you get me. As it increases, as technology increases, our ability to counteract the negative aspects of this technology is also increasing, because we are forced to do so. Just like I am pretty much forcing myself to learn about quantum computers in order to, you know, give you guys something to listen to, and also hopefully you take away some information too from us learning together. You know, you got to force yourself into these situations. That's why there's no way better than to force ourselves to solve this problem than to make sure that we get quantum computers done. And I assume within the next 10 years, to be honest, we'll have our first quantum computer that they're gonna say is the stable version, that beginning version, you know, like almost like an operating system, the Windows operating system, that stable, you know, everybody can start building, and we can start evolving from that, and other companies can start using that to create what they want to create, or what else. That is a long time in the future, but when we reach that point, we will have to take the necessary steps to counteract all the negative aspects of it, especially since we're in the stage right now where people are really understanding and educating themselves on security risks and privacy risks, and companies are pretty much putting their full effort into that, making themselves secure. Lack of security is an issue. So there's no way that when these things start coming out that people are not going to think, hey, let's prepare for the negative aspects. It's not going to be like when it was computers and being like, let's get this out to the public and then see what negative aspects come from it, and then we'll tackle those issues when we get there. No, I don't think we're going to be at that point. People have a different ideology or different concept of computers and technology. We understand the real issues that can come of it and the real benefits of it, and you know, we in some cases it may tip the scale here or there, but we know that we're aware of it. There's not that lack of knowledge. Maybe some areas of the world, yes, they don't have the amount of knowledge that we do when it comes to technology, but well, when it comes to computing technology, but right now we're at that stage where we can. So let's finish it up with this video, and then we're going to find something else to either watch or read.
Another really exciting new use is simulations. Simulations of the quantum world are very intense on resources, and even for bigger structures such as molecules, they often lack accuracy. So why not simulate quantum physics with actual quantum physics?
Makes sense.
Quantum simulations could provide new insights on proteins that might revolutionize medicine. Right now, we don't know if quantum computers will be just a very specialized tool or a big revolution for humanity. We have no idea where the limits of technology are, and there's only one way to find out. This video is supported by the Australian Academy of Science, which promotes and supports excellence in science.
Pretty cool. Nope, we just watched that video. That is a really small video by IBM.
Dan Olds here, and this is another installment of my HPC blog. I'm here at ISC 15 with a couple of very special guests. First one, who I guess shouldn't need an introduction, but for those of you who haven't been around the industry or aren't as deep in the industry, this is Bo Ewald, former CEO of Cray, former CEO of SGI, veteran of many a startup, and you're now the, what's your official title at D-Wave?
Well, that's a good question, Dan.
And that's
your boy has gotten some work done out there with that, like, full-on Botox.
Thank you. That's going to be our first question. That's what we're going to do.
Money will do it.
In the podcast here today.
So nominally, I'm the president, and then also help look after all of the customer activities.
Okay.
So really customer-related things.
And you know, to kick this off, you're at a point in your career with the experience you've had, you could do anything. You could do nothing if you wanted to, right? What is it about D-Wave and quantum computing that brought you back into this?
First, let me tell you a little story about careers, and this goes back.
You've had a couple.
I've had several, but actually, I was at a meeting. The story I was going to tell was probably from 25 years ago or something, and I was at a similar event as this, and was sitting there with Seymour Cray and Les Davis and someone else, and someone came up and said, you know, I was with these real luminaries, and someone came up to me as this young kid, relatively, and said, "Boy, you've had quite a career, Bo." And Seymour turned and he said, "He hasn't had a career at all, but he's had a heck of a lot of interesting jobs." and that is really the way I think about it, is that I have had a whole collection of interesting jobs. I've never thought, never had a plan, a career plan, or those sorts of things. But sitting around the fire, and so maybe I can help out.
Throwing an occasional stick on.
But by some definitions, I think it's getting to do interesting things with interesting people in interesting places, and that sounds a lot like what we're doing here.
What is it about this technology that attracts you to it?
Yeah, so that actually is, besides all of this baloney I've just been through.
No, but that was good.
The really interesting thing about the technology is that it is so different, it is so unique, that I think we're at the leading edge of a brand new paradigm for computing. And in fact, I believe that we have a greater potential to change the face of computing with what we're doing to D-Wave than we did at those great companies like Cray Research and Silicon Graphics.
Wow.
So I want to be involved in that. I've always worked on things that were at the state of the art, were interesting, were first-class companies, and I think
those were the years when you were at those companies.
Absolutely were. Yeah. So I think the same things. I think the same thing, but maybe even greater. There's greater potential to change the face here. But the reality is that with D-Wave today, it's almost like we're in 1952 or 1953 or something in the traditional computing industry, because our equivalent of the Fortran compiler hasn't been invented yet. Donald Knuth hasn't written books about algorithms.
Okay. Everything's roll your own.
It is. And the first, and when
that's exactly what we were kind of touching on earlier, guys. Before I know I don't mean to interrupt him, but it's almost like there's, when he says we're back in 1952 with this with quantum computing, it makes a lot of sense that we have all this information about how computers today, classical computers work, how to develop algorithms, how to develop translators, like that are translating languages, from assembly, from high level to assembly, from assembly to machine language. It's like they're starting from scratch in the sense that they have all that information is useful but almost useless in a sense. Like, we have all that information, but when you're applying it to a totally different way of computing, you're no longer representing things in ones and zeros only. You're representing things as both ones and zeros at the same time. All of those books pretty much, and their information becomes very one-sided. It doesn't help with this progression only. Yes, it can help with your knowledge when it comes to, oh, that looks familiar, I know something similar to that, let's tackle it in a similar fashion. Yes, maybe. But other than that, it's pretty much, I represented it. was speaking to my fiance earlier, and I had pretty much told her that I relate to it like developing electricity for the first time. It's like almost that revolutionary. It's that kind of jump. And similar to blockchain technology, I wouldn't put blockchain technology as that unfathomable, because it makes sense. It uses what classical computers can do. It uses that in a very meticulous and important way, like how we did. We spoke about this yesterday. If you guys didn't know, we jumped into cryptocurrency, and we kind of also dove into blockchain, as blockchain is cryptocurrency is pretty much the byproduct of blockchain, with an irony being that blockchain came from the first development of the first cryptocurrency, Bitcoin. But it's that with blockchain, we had classical computing, we had the resources to do it. With quantum computing, there are no resources to do it. It's pretty much all those things that we had are not going to work for this, so we have to reconceptualize and rethink how we do everything, or how they are used to doing things. It's no longer using that data to build this new version of machines. It's pretty much creating their own data. They are creating the scenarios and the situations and the technology to do this, to do quantum computing. Yeah, I just wanted to jump in there.
When does something on one of our computers, it is probably the first time that it's ever been done on a quantum computer.
Wow.
And that's exciting, interesting.
It is very exciting.
So we're not at the point where I can ask you have RAID on the motherboard of this?
No, you could ask that. and you
have
know
you
the
slap
answer.
me.
Yeah, right, exactly.
Well, we also have Murray Tom with us as well. And Murray's one of the young Turks, I guess, in this whole quantum wave, so to speak. What is it that captures your imagination? What's the potential of quantum computing?
Well, I originally got into the space after I'd seen a lecture from Geordie Rose in 2002. Yeah, I think that was probably closer to 2000, 2001.
When you were 14?
Yeah.
You really look young. In a good way. You're going to love that. That's going to be great for you. Isn't it? Oh, he's got it, yeah.
Yeah, that's right. And at that time, we were, when I got into the space of building quantum computers, I was excited about the idea of whether we could even build a machine or not. And actually, once we had built our first machines and Lockheed Martin purchased our first one, we had customers. You know, the great appeal about quantum computing is that what we can use it for. It's like a tool. So being able to put a tool in people's hands and seeing what they can do with it, I think has probably been really exciting. And
only
the
way to test it,
for,
to improve it.
Really powerful growth in this technology space,
Yeah.
allowing us to solve problems we haven't solved.
Pretty much what he's saying is that, you know, once they got the beginning process, that first, you know, primary quantum computer, nothing like, not a true quantum computer that, you know, that they can start dishing out and saying, yeah, this is the basis of all quantum computers. No, they're the first initial stages, and once they were able to give that off and test it, he realized the growth in it is that we need the testing, we need to break it and fix it to improve it. Same concept with classical computers, but on a totally different scale. They need to try and force break these, or force these things to put them in situations where they have to analyze the outcome more severely, and from that outcome grow the quantum computer, grow the quantum chip.
Before, I think is what's really exciting. Gets me out of bed from day to day.
But we're still at the point where we don't know what this tool is. Is it a hammer? Is it a screwdriver? Is it a knife? Right?
That's the also
you're finding new uses for
part
it.
of the exciting part. Yeah, exactly. It's sort of exploring new ground, and sort of peeling back the layers of what the technology can do, how to make it better, and finding the ways to put it into application. Yeah, it's you know, working on the most challenging problems. That's sort of what we talk about with our customers and partners. That's what we want to help them do, and that's also, you know, a big part of our own culture in terms of what we want to do and helping people out.
And I know that it's so early, there's no typical use case, but when you go into a customer, either one of you, what do you say? How do you start out that conversation? It's not, we've got quantum computers, you know, press hard on this PO because the fourth copy is yours. It's probably a bit more than that. How do you introduce the concept to them?
Well, let me first make a comment about Murray. As you noted, he does look young. However,
yes,
he is one of the senior members from D-Wave.
He's been around.
He's been with the company for a dozen years or something like that.
Yeah.
And you know,
again, starting when he was 12.
Well, exactly, and that's been one of the jokes that we had. In about a year or so ago, we were giving a thing to some customers in the UK, and I said those very words. I said, you know, Murray's a senior member. He started with us when he was about 12 or something like that. After the meeting was over, a fellow came up to both of us and said, "Did you really start with a company when you were 12? Here in the UK, we have labor laws, and you wouldn't be able to do that."
I would hope that you would have said, no, he was just an intern then.
Right,
that was his summer job.
Exactly.
He also mowed lawns and stuff, but he was an intern. Yeah.
But you know, but that actually is part of the point to the question you ask, and the technology that we have is so different that people my age have grown up with this other technology. It takes new, fresh minds to think about how to use this, and so Murray is a wonderful example of that.
In your briefing, it was really hard for me to get around this, because I keep trying to put things in terms of digital analogies to be able to figure it out, and it just doesn't work.
Exactly. So to your question of how do we talk with folks,
you know, he says, it's when he says that, you know, it's same for me. I'm not saying that I'm like old or nothing like that, but you know, I studied software engineering, and you study a specific way, you learn things a specific way. Everything is very logical. It's like you do it this way, it does it this way. There's of course there's abstract coding and stuff like that too, but even when you're doing abstract coding, there's still a logical pattern to how it works. There's nothing that is so beyond to understand. So when I'm hearing this stuff and I'm introducing this to me, it's really hard for me to wrap my head around for that same reason. It's that it lacks the logic, and you know, he really hits the nail on the head to say that you need the youngest minds in the game to really do it, because you need to have a fresh mind, a mind that isn't been exposed too much to the inner workings of classical computers, so that they have an interest in computing, but you know, they're interested in a new type of computing, which I find really interesting that that he mentioned that, which is really cool, because I think that's where the future should head. I always recommend to anybody that's younger than me, or you know, growing up, teenagers, I say, yeah, you need to get into software, you need to get into some form of computing, some form of technology, whether or not it's hardware, whether or not it's software. But now I feel like I'm going to change that up a little bit. I'm going to be like, yeah, you need to get into thinking about quantum computing, because if you really want to make it big in an industry, you might as well try going into an industry that is fresh, that there is a lot more room to discover. You know, that's not to say that software, there aren't, like, you know, software, you can come up with algorithms to do anything. You can come up with a new algorithm to do something differently and better than what was before, and make a great improvement and do a lot of work and do a lot of good things from that, which is, I'm not disputing that. But being in a fresh ground, almost, that anything you do is new. Anything you do has never been done before, like he said. Wasn't it Bowie or something like that? Anything you do is the first time it's been done. That's almost so interesting, and that it can spark that creativity, that change, that be like, well, if, you know, there's no no's as hard, as redundant as that was, there are no, we shouldn't do that, you know. They are, oh, let's try that, because, you know, from classical computing, we know what works and what doesn't work, and there's not a lot of room to go beyond that. There is room, but there's not an intense amount of room. With this, it's like, let's try this, and then no one is going to be like, no, that won't work. They won't know, because it's never been done before, and that's really cool. And I think this is a new wave, and I really hope that they start offering stuff like this, dedicated stuff for quantum computing, in lower level courses, and not just higher level courses like postgrad or you know, whatever, PhD students or anything like that. I hope that they start doing this for undergrads and stuff like that. Like, I would totally have loved to do a course on quantum computing. And I did physics. I did physics 1 and physics 2 in school, but I would have loved to do, maybe, you know, there was the option to do quantum physics, but maybe did quantum physics in a way that it directly correlated to my major. And that would be awesome, and I hope that the future has that.
Folks about this. Basically what we say is that we do have this new tool, and it has some really unique characteristics, and it's got some things that are going to make it really hard to use and a little frustrating for you. But what it looks like it will be good at are solving 3 classes of problems. A particular type of optimization problems, probably machine learning, which is what Google bought it for. And then thirdly, it looks like it'll be good at Monte Carlo and sampling sorts of things. But again, we're early days. We don't have the equivalent of
those are some
compilers.
pretty big niches.
Those are big niches.
Yeah.
But what we also say is that it's going to take a lot of work on your part and ours. It's going to take a real partnership for us to look at your particular problem and see how to sort of reconstruct it rather than deconstruct it, but go back to the basic problem you're trying to solve and be able to put it on this engine and see if we can solve it.
But if that works, we're not talking about, you know, solving a problem twice as fast or 3 times as fast. We're talking about orders of magnitude, right?
We are. And we don't have many examples of that yet, but the first and probably the best one of those today came from Google. So before Google bought the machine, they wanted to solve, they asked us to work with them and sort of run a set of 2 sets of problems. One were benchmarks, which you and I would call performance characterization, as opposed to a customer-oriented benchmark. It was really performance characterization of the machine. And so they gave us a set of synthetic benchmarks that were aimed at sort of figuring out the performance envelope of this machine, much like LinPack might be in the HPC world, but not as sophisticated as LinPack. And then they wanted to run those on commercial off-the-shelf optimization software, which they did. So when we ran those at small problem sizes, we were losing, the traditional machines were 100 times faster than we were. When the node size got up so that it was about 100 qubits on our machines, we and the traditional machines were about equal.
So as it scaled.
And then as it got larger, and at the time we were testing on a 500 qubit machine, we in fact...
Wait. Did he just say 500 qubits? You know, maybe I should have started at this video, because the video that we first started on with the expert going through the 5 levels of difficulty, the quantum computer that they're referring to only had 50 bits. And she said that was amazing. They're telling me that they have quantum... I'm stopping this right now. D-wave quantum, that's just normal D. Quantum computer number of qubits. What? Guys, that is a jump. Now, they say they're going to need millions, which is reasonable. But 2,000, you know, we just watched a video that was how old? Let's see how old this video is. Came out June 25th of 2018. This is IBM's. Yeah, this is IBM's computer. And you're telling me that D-Wave is gotten a quantum chip with 2,000 qubits? If y'all don't see that rapid growth, I don't know what else to say, because if at that rate, if you did, that's back in 2016, that's no way. What is going on? A 15 million, oh yeah, that makes sense. And how much it costs? The D-Wave 2000 is a firm first 2000 quantum bit computer. Okay, wow. So I'm guessing that IBM is like really behind on this, and D-Wave is the forerunner for quantum computers. Wow, 2000, and that's back in January of 2017. So guys, if you don't see the exponential growth, if 2000 is that rate, let's say 10 years from now they could be up at 500,000, and they say they needed just millions or a few million of them to really be at that peak potential. That is very reasonable and reachable within 15 years. Wow. This is incredible. I'm glad I stumbled upon this interview. Guys, I'm going to take a quick washroom break. I'll be right back in 2 minutes. Oh, that's okay, Pineapple. I was wondering, man. I was like, haven't seen you in the stream. I was actually kind of surprised. We did some learning about quantum computing, so I just had to take a little break just now and go use the washroom. But yeah, I'm back. Gonna be back for another 44 minutes. Hope you're doing all right. Thanks for bringing Laundrette into the stream past couple times, man. I do appreciate the support. But yeah, so we've just been listening to this guy, you know, give us some info about quantum computing. This is actually one of the heads of D-Wave, which I didn't know, but is pretty much the leading force in the quantum computing world. They sold quantum computers to both Google, Google, and I think it was a couple others. I can't remember. It was Google. He mentioned two others that he had sold to, but big names. Google being the biggest, of course, for 15 million, which is not reasonable. But yeah, so these are the big boys in the business. So I want to learn a little bit more about what they had to say. So we're just gonna finish up listening to this interview, get a little bit more knowledge from them, and then maybe, you know, head off and do a couple of fun things before we turn off the stream today.
1,000 times faster.
That's not bad.
Now
that's a win.
That was
that's a win.
Yeah.
Sure.
That was again
one test, one case,
one benchmark, a point in time.
But put to you by some fairly sophisticated folks.
Yeah, you would think
it's not spec in.
No. So, and we think
there's
that
some promise there.
There is promise, right? Exactly. So I think that really was what got Google and others' attention is, gee, if you really could map a problem onto this. Mm-hmm. Again, these were synthetic benchmarks.
Sure.
They weren't their real application. They were tuned to be able to run well on this machine. But that shows the promise of it. And then in the intervening 2 years, in fact, we just at this conference been showing some people how by interpreting the problem a little differently, Murray and his team, in fact, have gotten us now so we're even faster than that compared to those original benchmarks.
And one of the things that Murray brought up in the briefing that we had was the hockey team problem. It's an example of the kind of problem that this is good at. And if I could summarize it, that it's along the lines of, let's say you have a universe of 2,000 players and you need to pick the best hockey team, and you're going to look at variables as to how each individual player plays, but also how do they play when they're matched with these folks or against these other folks. And you keep adding more and more variables, and you can take it from here as to what quantum computing has to offer for that kind of problem.
Yeah, so the interesting thing about the technology is to think about it as sort of like solving a very particular problem. So what, as you were saying in the hockey team example, part of what makes that difficult is that when you're selecting a player to be on your team or off your team, you can't use a weight. You can't take a part of the player. They're either there or they're not. Mm-hmm. And that basically makes the search space very large. It's combinatorially large. And if the hockey players didn't interact with one another, it would be easy because you could just do sort of independent assessments of each player.
Yeah.
But it's the relationships between them, the correlations there, that link the search space.
Remember, guys, we talked about those correlations in the beginning. We went through that article that spoke about the correlations.
And make it very challenging for classical computers. And one of the features that the quantum processor can do that no classical technology can do is it can begin by searching the entire solution space simultaneously and then very quickly converge, localize on a team which is a very high quality team. And it does that by, and we often refer to it as, it's a minimization task. So it's searching the landscape of all the possible teams it could be choosing and finding the low point in that landscape. So if you think about the chip as sort of like a quantum experiment, that quantum experiment is minimizing its energy.
I want to see this. Processing using the D-Wave chip. A lattice of superconducting loops called qubits, chilled near absolute zero to quiet noise. So is that why they chill it? I guess, man, they must have threw me off with that 5 levels of difficulty video. But yeah, so they chilled it to near about zero to quiet the noise. So I'm assuming it's extremely loud. I thought that it would overheat or something like that. User maps a problem into search for the lowest point in the vast landscape, which corresponds to the best possible outcome. processor considers all possibilities all possibilities simultaneously to satisfy the network of relationships with the lowest energy. The final state of the qubits yields the answer. So that's really where I'm seeing more of that tie with quantum physics than in the previous explanations, is where it says processor considers all possibilities simultaneously. So it considers, as the example that our interviewer was using for a team, a hockey team versus another hockey team, the processor has to consider all matchups with every team. It can't just assume what is going to be the outcome for just that one team that you're considering it for. No, it has to consider the outcome for all of the players in that team, you know, off bench, off season, on season, those kind of things. People that are on the bench may swap out substitutions, that kind of stuff. And as in addition to that, it has to consider all the other teams that it could get matched up with. So that's where the quantum physics. Remember, guys, I used that example where you go into a bar. Quantum physics dictates that if you go into a bar and you order a drink, you are going to have to consider every option of drink that you get. You may say, I order an orange juice, but quantum physics dictates that you have to account for every single other drink that you may get. The bartender may not hear you, may give you apple juice, may give you a beer, may give you something of the sort, but quantum physics dictates that you have to consider every single one of those possibilities, and it considers them simultaneously, you know, until it reaches that outcome, until you've gotten that drink. You know, you may have got the beer, but guess what? That wouldn't be new news. That wouldn't be new news. That wouldn't be some different news for you. That would be common. You would have known about that possibility. You could have taken that possibility into consideration prior to ordering the drink. You would have said, oh, there's a chance I may not get this orange juice, and then there's a chance I may get the beer, and it just so happens that you got the beer. So it was easier to map that conclusion because it was already perceived. And I think that's where the main goal for quantum computing is, like, once using quantum physics, that's the main aspect of it, and that's where I really see them using that to solve tasks, to almost remove the probability. Well, there's going to be probability, but removing the statistical data from predicting outcomes, where we use statistics and past data to predict future data. And essentially, no, we're going to just predict future data based off of the data that we're seeing right now. Where we are right now in this current moment, we're gonna predict what can happen, and you know, we may get to that end result.
Interesting. And from there, I mean, every time you add a parameter, you're exponentially making the problem more difficult.
Yeah.
Yeah, that's the amazing part. And when we turned down the first D-Wave 2 machines with 512 qubits, there was sort of that moment where we realized, you know, this is searching a solution space that's larger than the estimated number of particles in the universe. So I find that's just
large.
That's very mind-blowing, yeah.
That's very large. Very interesting stuff. And there are some hurdles that customers need to get past. They need to be able to define their problem.
Yep.
The machines are not desk side, I wouldn't say. And I thought one of the really interesting technologies that I think you folks at home will enjoy, particularly the register readers, is that the processor's kept at minus 459 degrees Fahrenheit.
That's correct. Yeah.
So it superconducts at that temperature.
That's right. That's right. The quantum world is a very delicate world that's easily disturbed. So in order to make a processor that can perform these powerful calculations, we effectively need to separate it and isolate it from all forms of noise and disturbance, and temperature is one of those forms. So it's housed, you know, in an ultra low temperature refrigerator, and the nice condition there, as you were saying about the superconductivity, is that the processors that we're used to running in our laptops and our phones operate at room temperature, and when you turn them on, they heat up. In this system, the operating temperature is a very low temperature, but when you turn it on, because of the superconductivity, it doesn't produce any heat in the processor.
Interesting.
And in fact, Dan, you know, when you look at our systems and the images that folks will see of the systems, they look large. The container is about 10 feet by 10 feet by 10 feet.
Yeah.
And for Murray, that's 3 meters by 3 meters by 3 meters, but about a cube that's about 10 feet. The computer, the processor itself, is no bigger than your thumbnail.
Exactly.
And that's sort of right at the heart of it. So this whole the system that you see is filled mostly with air. And we built
That's
it that
the crazy
size so
part.
that in fact we could have, as we're working on it, we could have 2 or 3 people in working on the refrigeration of the system.
So it's completely electrically isolated and shielded and thermally.
Exactly. And so shielded from radio frequency, we have to cancel out magnetism, we have to do a whole variety of things because, as Murray says, it is.
It's a huge bunch of engineering work.
So that's really incredible that, you know, one of the biggest hurdles for it is not the adding more, well, yeah, of course, adding more qubits to it to make it be able to incorporate all those different variables. You know, remember what the guy said, you have to take into account every single aspect, and what I said as well, you have to take into every single possibility, and as soon as you start doing that, things start to grow drastically. So you think, okay, yeah, you just need more qubits, work on adding more qubits. But as you're adding more qubits, you're also needing to improve how you're housing the processor, so make sure that it has none of these interference, such as there's no issues with the temperature, radio frequency, magnetic sort. Well, that's polarization, anything like that. Because remember, guys, the superposition refers to it either being spinning up or spinning down, where it could be where it represents the different levels of polarization. So obviously magnets, a magnetic field being involved inside one of those things could affect it negatively, you know, make it have, you know, not have the results or do what it's supposed to do. So I think that's really cool that the largest and most sophisticated portion of it right now is not even the chip itself. It is the machinery around it that is allowing the chip to function. That is really cool, and that's probably where most of the money is coming from. Obviously the research pays for is what's quite costly for the building the chip itself, but I see a lot of it being the price is coming from the machine that is housed in, having it to be made of solid gold. You know, well, all the mechanisms in it is solid gold because it can reach those kind of minus 400 degrees Fahrenheit temperatures, or 400 Kelvin, sorry. That is fascinating to me. That is that's the primary hurdle that they're facing right now, is making sure that there's no interference, that these particles are completely isolated. There are no instances where you're having issues with, you know, no radio waves are getting to interrupt anything. One thing that kind of brings to mind is, why not conduct these in space? I know that seems kind of like far-fetched to be like, yeah, well, they should just build them in space. But yeah, maybe they should build them in space, because space, you know, there is still radio frequencies, so you'll still have to watch out for radio frequencies, but there's less magnetic interference, zero noise, because you're in the vacuum of space, where you can't really, you know, there is no noise out there. And then it's freezing. We all know that, yeah, space is very freezing. So I do see that maybe I'm surprised that they haven't like just focused on building those things in space, but I guess that is a very costly thing to do as well, so you're not really saving on cost because it's not cheap to get these kind of things in space. So I guess, you know, it's a hit or miss there. But I would like to see, you know, we reach that point where they're developing these things on international space stations, or just around the International Space Station. I think that would be really cool. I'm not sure if that's how they're doing the communication between the isolated particles that my boss had mentioned to me today, about how they're able to communicate from 1,000 kilometers away from a satellite to on Earth in such a fast motion, because the particles are correlated, they are entangled, they have been had some sort of reaction to each other, that they are forever entangled once they are completely isolated from magnetic fields, from radio waves, and from temperature or noise disturbance. Now, that is, I can see where that's applicable, because the one in space makes sense, but also because they obviously they wanted to test the speed over distance. But wouldn't that be really useful then to use these in space exploration? You know, I'm assuming that is probably one of the things that they want to use it for. But like, if you put these on a satellite, you know, I think, isn't it true? I'm not a astrology, or, you know, what is the word, an aerospace engineer, but I do know a few, and I actually am going to be interested in asking them this question. It just came to my mind that a large issue with you know, radio frequency and radio waves is that it takes time for them to reach. You know, they can reach the longest distance on the spectrum, on the can't remember what it's called. It's not light. It's ray spectrum or something like that. Where there's like X-rays, gamma rays, radio waves, all that kind of stuff. The wave spectrum, for lack of a better word, probably it is that. But yeah, in that terms, radio waves can travel a long distance, but they take a long time. They only travel at a certain speed. While this clearly, quantum computing can travel at a much. Quantum computers or quantum particles can communicate at a much faster speed. So wouldn't that make sense that instead of relying on satellites to bounce images from one satellite to the next, to the next, to the next until it reaches back to Earth, wouldn't it make sense to, you know, push that satellite out with that quantum computer on it? And I know this is not something probably that they're doing right now, or they may be doing it right now, I don't know. But that seems really like a really suitable use. And I know that right in this current day and age, we're not doing as much space exploration as we used to. But I hope that Elon Musk is jumping on this, and I'm sure he is, because he's money fountain. And also, I see how this can possibly apply to the self-driving cars. I don't know. Maybe, you know, it could allow them to make the necessary calculations that can improve the efficiency and reliability of the self-driving cars. We don't know. But I do like that they could possibly use this in space exploration. That distance, that ability to communicate over such large distances at such a fast speed, that, you know, could improve a lot of things. We wouldn't rely on the speed of light anymore. Or speed of radio waves. We would rely on the speed of communication between quantum particles. That's really cool to me. I don't know.
A tremendous amount of engineering has gone into it. So the physics is impressive, and the engineering and manufacturing technology are equally impressive to be able to do that. But the reality is the system itself really is no bigger than your thumbnail.
Yeah, I saw that. Just a very tiny
chip. Looks like a regular chip that we would see. It's got a couple of special characteristists to it.
Yeah, there's some secret sauce.
Yeah, there's some secret sauce.
But this has just been fascinating, and I assume that if anybody goes to the D-Wave website, they can see more. And throughout this talk here, I'm going to be having some slides just to give people a little bit more information. But best of luck to you two, and thank you for taking the time. Great stuff.
Thank you, Dan. Appreciate the interest, and those of you who are listening, really appreciate your taking the time to look at what we're doing. It's great. It is revolutionary.
It is.
And it is going to change the face of computing, we think, more than some of the historical companies and technologies have.
It certainly seems like it has that promise.
Great.
Thanks again.
Thanks so much, Dan. Appreciate it.
It's awesome. It's actually pretty cool, man. But yes, so we've discussed quantum computing for the past 2 hours. Sorry for the stretch, but had to do it. So now we can look at, you know, either playing a couple games, which could be fun, or we could do some more research into it. So it's entirely up to you guys. If you'd like to see more about quantum computing, we could look into some more stuff about it. Maybe even dive further into D-Wave, since seeming as they are the leaders in this area. Or we can look into some games. We could play around a couple games together. So you just gotta let me know. All you gotta do is say something in the chat for me. Let me know what you want to see. And in the meantime, I'm gonna play this scribble game. What's it called? Quick draw. Play a couple rounds of this because it's fun. Speedboat. What? Oh,
I see canoe.
I'm terrible.
Or ocean. Or string bean. Oh, I know, it's speedboat. I see rainbow. Or parachute. Or umbrella.
How much?
Or helmet.
Wait, how much?
I see mushroom. Or water slide.
Oh,
or
this is terrible. This is terrible.
Or computer mouse.
I give up on that one.
I see nail.
I had to cover it up.
Or
I
comet.
had to cover it up.
Or foam finger.
I couldn't even remember.
Sorry, I couldn't guess it.
I tried to draw a spider there by mistake instead of a octopus. That was beautiful. Alright, candle. This should be easy.
I see diving board. Or skyscraper. Or hockey stick. I see snorkel. Oh, I know, it's candle.
Alright, boomerang.
I see garden hose. Or mountain. Or umbrella. Oh, I know,
Look
it's
at that
boomerang.
boomerang, guys. That's. Oh my gosh, I just lack.
I see knee. Or circle.
I see knee.
Or moon. Or potato. Or blueberry. I see hula hoop. Or bracelet. Or onion. Or cookie. I see steak. Oh, I know, it's compass.
Yes. Alright, so a leg.
I see line. Or nose. Oh, I know, it's leg.
Look at that leg. Oh, this is absolutely terrible. A stereo, I can do that.
I see diving board. Or pillow. Or bench. Or keyboard. I see camera. Oh, I know, it's stereo.
A lion? How do I draw a
I
lion?
see toothbrush. Or garden hose. Or arrow. I see arm.
Well,
or
this is-
giraffe.
I don't know how.
Or dolphin. Or cow. Or fox. I see bat. Or dragon.
I can't draw that.
Or raccoon.
Who can draw a lion? Like,
Sorry,
what is this?
I couldn't guess it.
Underwear.
I see line. Or ocean. Or canoe. Oh, I know, it's underwear.
Looks like a whale's tail, man. A mermaid. Alright.
I see string bean. Or foot. Or dolphin. Or arm. I see banana. Oh, I know, it's mermaid.
That is terrible. Oh, computer. I'm gonna draw a quantum computer. I joke.
I see elbow. Or suitcase. Or square. Or dishwasher. Oh, I know, it's computer.
Look at this. A diving board.
I see bench. Or keyboard. Or eraser. Oh, I know, it's diving board.
You can't mess me up. Look at that quality. It gets harder, by the way. Alright, so watermelon.
I see volcano. Or circle.
How am I gonna draw a
Or
watermelon?
moon. Or basketball. Or onion.
Okay, well.
I see bread. Or baseball. Or mouth. Oh, I know, it's watermelon.
Yes, the Great Wall of China. What?
I see line. Oh, I know, it's the Great Wall of China.
Okay. Okay.
I see circle. Or moon.
That is the
or
worst
frying pan.
bicycle ever.
Or dumbbell. Oh, I know, it's bicycle. I see broom. Or string bean. Oh, I know, it's carrot. I see rainbow. Or the Great Wall of China. Or shoe. I see peanut. I see pond. Or whale. I'm stumped. I have no clue what you're drawing.
I have no clue
Sorry,
what
I
you're
couldn't
drawing.
guess it.
That is terrible. What was it? A bench? Oh no.
Oh, I know, it's bench.
Oh, how did he know it was a bench? This is pretty much just an intelligence neural network that's trying to learn from me draw. So let's draw a church.
I see line. Or knee. Or stairs. Oh, I know, it's church. I see stairs. Or remote control. Or door. Or cell phone. Oh, I know, it's calculator.
Alright, a nail. Alright.
I see line. Oh, I know, it's nail. I see bench. Or keyboard. Or eraser. Or pool. I see sleeping bag. Or toothpaste. Or piano. I see marker. Or crayon. Or cooler.
China!
Sorry, I couldn't guess it.
A bat? What kind of bat?
I see string bean. Or garden hose. Or spoon. I see baseball bat. Or feather.
Oh, is it
Or
supposed to be like a
clarinet.
bat? Like a...
Or baseball. I see diving board. Or giraffe.
Oh, that's terrible.
Or foam finger.
A foam finger?
Sorry, I couldn't guess
I
it.
did this one before.
I see toothbrush. Or canoe. Or keyboard. Or eraser. I see pencil. Or marker. Oh, I know, it's speedboat.
This is terrible. I can't be playing these drawings. That is absolutely dreadful. Can't be playing that anymore. Okay, so we got about 15 minutes left in the stream. Let's find something else. Maybe let's play a game of Hearthstone. I haven't played that in a while. We're on a little Hearthstone, guys. If you're now jumping in the stream, we pretty much just spent the whole stream talking about quantum computing. I'm just going to take a little break for the next 15 minutes, and we're going to play a game of Hearthstone. If you guys aren't familiar with it, it's really easy to play. It's a card-based game, kind of like, I don't know, Yu-Gi-Oh! or Pokemon or something like that. It's really basic to play. But yeah, that's what we'll be doing today for the rest of the stream. Only about 15 minutes left. Gonna play some people. If you guys do have an account, please comment in the chat and let me verse you. It's like, yeah, don't worry that you're trying to find a game quick for your stream. We're gonna take the longest that we've ever taken to find a player. No, it's just Murphy's Law for you.
Jaina versus Rexa.
Let the hunt begin.
You asked for it.
Quickly. Handle it!
What to do? What to do? to do? What to do?
Get behind me.
Job done.
I wonder.
Ooh, this is not going too well for me right now.
I wonder.
Someone call for the doctor.
I let the dogs out.
Hmm. Oh no, I didn't. Oh, wow. Why would I do that? Why?
To my side.
Wow. It's not looking so hot for me right now. And I'm not getting any of the cards that I really need right now. I need something to just pretty much wipe out this dude.
I wonder.
Oof. That's a concede. That's a concede. Sorry guys, just making a couple notes for my next stream. I'm not gonna bother playing another game of this. The first game didn't go too well, and clearly that's a sign to not play anymore. But I'm gonna end off the stream a little bit earlier today. We did start on time. I've been running over stream past 2 days, so I wanted to get a little bit under today and get head started on tomorrow. We'll be heading over to Twitch, so please tune in for Twitch. It won't be on YouTube. It's gonna be the same. Techgician. You just gotta search for me on Twitch. Give me a follow, please. I would really appreciate the support. You guys are awesome for spending the time today to listen to me. I hope you learned something. I know that I learned a lot of stuff about quantum computing. Hands down, much more. I came in here with not the knowledge that I'm leaving with now, and I am glad that I was able to do so, and I hope you guys have learned from it as well. But that's pretty much it. We don't have a set topic for tomorrow. I kind of wanted to go into Twitch and kind of feel out some stuff and talk with you guys, and have an opportunity to communicate with you guys rather than have a set of topics. I wanted to have something. I'm going to go in there. Of course, I'm going to come in with some topics, but I'm not going to set them and establish them as a guarantee, because I do want some people to come in and kind of influence our topics for the day tomorrow. So please check into Twitch, the Techgician. All you gotta do is search Techgician in Twitch, twitch.tv. Come and join us from 1:30 to 4 o'clock. I'd really appreciate the support, man. And as always, peace. Everybody have a great rest of their day, okay? The weekend's almost here.